This video is about session 7.7, comparison of improper integrals. Often we can tell whether or not an improper integral converges, even when we cannot find an antiderivative. This is done by comparing the improper integral with that of a simple function. Before we start this section, we review two important improper integrals that we did in last section. The integral of 1 over s to p x from 1 to infinity dx. This integral converges for p greater than 1, divergence for p less than or equal to 1. Another important improper integral is the integral of 1 over x to p x from 0 to 1 dx. This integral converges for p less than 1, divergence for p greater than or equal to 1. Now let's look at an example. We look at the integral of 1 over square root x cubed plus 5 x from 1 to infinity dx. So when x is very large, x cubed plus 5 is also very large compared with 5. So we have 1 over square root x cubed plus 5 is approximately equal 1 over square root x cubed. This is 1 over x 3 over 2. So this suggests that we compare with this function 1 over x to the power 3 over 2. So now we know this one 1 to infinity 1 over x 3 over 2 dx. This integral, so this improper integral, from here we reviewed we know p is 3 over 2, so it converges. So this improper integral converges. Since p is 3 over 2 is greater than 1 and has a value 1 over p minus 1, so 3 over 2 minus 1, so this is 2. Also, we have for x greater than or equal to 1, 1 over square root x cubed plus 5. This is greater than or equal to 0, less than or equal to 1 over x 3 over 2. So from here, we can conclude that for any b is greater than 1, so this integral, the integral of 1 over square root x cubed plus 5 s from 1 to b dx less than or equal to the integral of 1 over x to the power 3 over 2, 1 to b, this is greater than or equal to 0. So we have these inequalities. So we know this one converges as b goes to infinity. So it then follows that the integral 1 to b 1 over square root s cubed plus 5 dx must have a finite limit as b goes to infinity. Since it has a finite limit, so this improper integral converges. And in fact, we can see that the integral 1 to infinity 1 over square root s cubed plus 5 dx greater than or equal to 0, less than or equal to 2. So this is the first example. Next, we summarize the comparison test. For the improper integral a to infinity fx dx. So let fx is non-negative function. The comparison involves two steps. First, we need to guess. How to guess? So we can look at the integrand for large x, what the integrand behaves like, and whether it converges or not. This gives us a function to compare the integrand with. So the second step is to confirm the guess by comparison. So if we have fx less than or equal to gx greater than or equal to 0, and the integral a to infinity gx ds converges, then the integral a to infinity fx dx converges. Next, if we have gx greater than or equal to 0, less than fx, and the integral a to infinity gx dx diverges, then the integral a to infinity fx dx diverges. Let's look at another example. The integral from 1 to infinity sin x plus 3 divided by square root x dx. We know sin x is always between -1 and 1. So sin x plus 3 less than or equal to 4 greater than or equal to 2, then divided by square root x, here x greater than or equal to 1. So we keep the direction. So this is square root x, this is greater than or equal to 0. We know this integral, the integral from 1 to infinity 2 over square root x dx divergence. Then we have the integral from y to infinity sin x plus 3 over square root x dx, also divergence by the comparison test. Here note that the fact this sin less than equal to 4 over square root x is of no use here, so we only use this inequality, right? Since the integral of this function from 1 to infinity diverges, then we can get sin x plus 3 over square root x. From x from 1 to infinity, this integral diverges.